All right. Linearity of the Laplace transform. Okay, as you see in the previous video, and also Laplace transform is, what is it? Linear. So using linearity, actually, we can solve a lot of differential equations much easily. Okay. Why is it linear? What do you mean by linearity? That means that actually from linear algebra, it's exactly the same thing. That means that I have to show that this Laplace transform of two functions, let's say alpha times f, that's our function, that's constant, plus beta times g, and let me just write here f of t and g of t. All right, that is equal to actual Laplace transform of linear combinations of two functions is equal to the linear combination of Laplace transforms of these two functions. It means this. Why? Because using the definition, what is it? I can write it as using a definition from 0 to positive infinity, e to the power st. Here we have the function. What do we have here for the function? Here we have alpha times f, let me just not write t here, plus beta times g, right? Here we have dt. And using the property of integral, because we know that integral operator is linear, right? I can just separate them. And also this alpha is constant. I can take this out. So I can write it as alpha times from integral from 0 to positive infinity, e to the power st. And here we have f. Plus, how about here? B is constant. I can take this out. Here we have b times integral from 0 to positive infinity. Right, here we have e to the power st, because it's a common factor, also multiplied by this, times here we have g of t dt, right? And that is equal to what? And that is just equal to f of s, right? This one is g of s, right? So that's why it is linear. Now using this linearity, if you saw example A, question A, find the Laplace transform of this function, 1 plus 5t. Okay, so I can write it as Laplace transform of 1 plus Laplace transform of 5t. 5 is constant, I can take this out. So here you can write it as 5 Laplace transform of t. And what is the Laplace transform of 1? That's equal to 1 over s, plus here we have 5 times. And how about the Laplace transform of t? That's equal to 1 over s squared. Or that's equal to s plus 5 over s squared. Okay, another example, how about B? And also in similar way, this thing, I can write it, let me just continue here. I can write it as 4 times, because it's a constant number, Laplace transform of e to the power 5t, right? Minus, and 10, here we have Laplace transform of sine of 2t equals 4, here we have 4. What is the Laplace transform of e to the power 5? That is just s minus 8, right? That's equal to, here we have 4 over s minus 5, because here a is 5. Minus, here we have 10 times. How about Laplace transform of sine of 2t? Here we have k, that is 2, over s squared plus k squared. That is s squared plus 4, right? Or I can just write it here, it is 20 over this, and you can simplify this. All right, that is how actually we are using or making use of the linearity of Laplace transform. All right, guys, I think you got some idea about this Laplace transform. Now we can just write here a few of them. And the first one, we already calculated this, right? And also this t to the power n, this b, you can actually prove this using, what is it? Using this formula, Laplace transform of t to the power n is equal to, here we have n over s times Laplace transform of t to the power n minus 1. Okay. And using this formula also you can prove this, you can practice this. I'm not going to do this. Okay, it's not so difficult. And also e to the power at, we have already got this formula that's equal to 1 over s minus a, right? And how about sine of kt? We also already calculated. That's equal to k, I'm using the definition, k over s squared plus k squared. And also in a similar way, you can evaluate the Laplace transform of cosine of kt. And here we have s over s squared plus k squared, sinh kt, or sinh of kt, that is k is similar thing, but the difference is minus, right? But it is cos, it is also, here we have plus, and here we have minus, right? And this hyperbolic functions, and sometimes we are going to use this, and also you can have a look at your calculus book, how they are defined. This sinh and cos, it is just, how to say, it's just compact representation of the combinations of e to the power t and e to the power minus t, right? That is equal to, for example, sinh of kt. What is it? It is e to the power kt minus e to the power minus kt over 2. How about this cos of kt? That's equal to e to the power kt plus e to the power minus kt over 2. Okay. All right. Now these things, actually proof is also beautiful, but I'm not going to prove them here because it's going to take a lot of time. We don't have that much time, but I'm thinking to make a video on proving this stuff and share with you. I'll see, okay? But here, you just try to understand and read it and continue. So sufficient conditions for existence of Laplace transform of f of t. Right now, okay, because we are evaluating here, all right, we can find this. Now the question comes, does every function has Laplace transform? Okay, the answer is no. I guess I feel really hot. AUC is on, but still it is hot. Let me just turn on my small fan. Okay. So the question is, does every function has Laplace transform? No. Sufficient conditions guaranteeing the existence of Laplace transform of f are that f be piecewise continuous on this interval from 0 to positive infinity, and that f be of exponential order for t is greater than capital T. Okay? For the function f to have Laplace transform, actually, we need to make sure that these conditions are satisfied. The first one is f be piecewise continuous on this interval. All right. And also from calculus, you should remember this piecewise continuous means if you're given any interval, right? If I just divide this interval into finite and many subintervals, and over each subinterval, if the function is, what is it, continuous, then we say that it is piecewise continuous. Maybe at this point it is not continuous. Maybe at this point it's not continuous. But if you just take some intervals, we have finite, I can divide this interval into finite many intervals so that over each interval the function is, subinterval the function is continuous. Then we say that the function is piecewise continuous over the given interval. All right. And the second thing here we have, and it says that f be of exponential order for t is greater than capital T. All right. So what do we mean by exponential order? Okay, that's the definition. It says that a function f is said to be of exponential order if there exists constants c and m, and these are positive, and t is also positive, such that this absolute value of f is less than or equal to capital M times e to the power ct for all the values where t is greater than t. All right. What does it mean? It means that after some points, actually, this function, this exponential function m times e to the power ct, it grows much faster than this f. Or in other words, this f grows slower than m times e to the power ct. Then if it is so, we say that this function is of exponential order. Okay, that is how it is defined. Because some function you will see that it is not of exponential order. For example, e to the power t squared, for example. Now we will see an example. Okay, the functions f of t equals t, f of t equals e to the power minus t, and f of t equals 2 times cosine of t. They are all of exponential order because the first one, here we have e to the power t. What is capital M here is equal to 1. What is our c? Also is equal to 1. And that is the graph of function t, right? And starting from 0. And as you see here, it is growing much faster than this function. If you compare this at this point, right? It is much faster. And that's why this function is of exponential order. How about the second one, e to the power minus t? That is the graph of e to the power minus t for all the values of t, I mean non-negative values of t, right? Because when we talk about Laplace transform, we just consider this interval from 0 to positive infinity. And here this is our function, for example, e to the power t. What is our capital M is equal to 1 and c is equal to 1, right? So I can find such numbers, capital M and c. As you see here, it is much bigger than this function. Actually, this is also that we say that this e to the power minus t of exponential order. Okay, how about this function 2 times cosine of t? That is the graph of this function, right? And we know that this 2 times e to the power t, it grows much faster than this function over this interval from 0 to positive infinity. Okay, sometimes it is 0 to positive infinity. Sometimes it may be from 3 to positive infinity. And that's why actually this capital T is positive. It can be any number here. Okay, because sometimes we may have the function something like this. Okay, when you just split this into 2 or 3, then we will consider them separately. Some examples for the functions who are not exponential order. For example, okay, not this one. Determine if the following functions are of exponential order or not. Okay, here we have t cubed times sine of t, right? And e to the power t cubed, t to the power 4, e to the power 6t, and t squared, for example, something, and these numbers. I'll just leave this as an exercise for you. Let me just do one thing, for example. Here, b, right? Here our function is f of t is equal to e to the power t cubed. Okay. So can you just find for some t, but here it is any number, right? For some t, so that this our absolute value of f, that is e to the power t cubed, is less than or equal to m times e to the power ct. All right. So can you just find any interval, that is any interval from t to positive infinity, right? Can you just find any positive infinity so that this inequality holds? Okay. Actually, if you just try to draw this graph, this t cubed, right, after some number, it grows much faster than this. So whatever you choose, this capital M and C, right, actually it cannot be greater than this over some interval from capital T to positive infinity. So that means that this function is of not exponential order. Okay. In a similar way, you can do this. For example, sine of e to the power t squared, right? It is just sine of something. It is bounded, right? It is, what is it? Maximum value is 1, minimum value is -1. So that is of exponential order. And also e to the power sine of t, the sine of t is always less than or equal to 1. And also this one is of exponential order. But this one is not exponential order. Okay. Sufficient conditions for existence. Now we say that if that f of t is piecewise continuous on this interval and of exponential order, now we know what we mean by exponential order, then Laplace transform of this f exists for s is greater than c. Okay, so if it is piecewise continuous and of exponential order, then Laplace transform exists. Now we may actually give a try to find it is Laplace transform. Okay, and also actually I will omit this proof. I may share it with you later. So transform of a piecewise continuous function. Now if you look at this, f of t equals 0 over this, right, is equal to 2 over this. And also we see that this function is of exponential order, right? It's just constant functions. And it's just piecewise defined function. So if you evaluate this Laplace transform of this f of t, that is equal to, using the definition from 0 to positive infinity, e to the power st minus st times f, right? And here we have dt. But f is defined differently on different intervals, right? And by using the, what is it, property of this integral, I can just split this interval, right? That is equal to from 0 to 3 e to the power minus st times over this interval. What is the value of this function? Is equal to 0. And here we have dt plus from 3 to positive infinity, right? Here we have minus e to the power minus st over this interval. What is the value of the function? Is equal to 2. So here we have 2 dt equals, and this thing is equal to 0 because of this, right? Is equal to 0. And if you evaluate this, take this to out, right? How do you differentiate this? That's equal to minus 2 over s times e to the power minus st from 3 to positive infinity, right? And equals from here minus 2 over 3, right? And here we have e to the power minus st. When t goes to positive infinity, that will be equal to 0 if s is positive. So if assume that s is positive, here we have 0 minus, if t is equal to 3, here we have e to the power minus 3s. Right? So that is equal to, here we have minus is plus, so here we have 2 times e to the power minus 3s over, this one is s, this one is s. So here we have s. Here s is positive. Okay, this is how we evaluate or find the transform of a piecewise continuous function. All right. So behavior of f of s as s goes to positive infinity. This is also a theorem, and also proof is beautiful. But here also I will omit, unfortunately, and also I'll try to make a video proving these theorems and share with you. This theorem says that if f is piecewise continuous on this interval, now see here in every theorem we are adding this condition. If f is piecewise continuous on the interval from 0 to positive infinity and of exponential order, okay, the second condition, and that f of s is equal to this. That means that, let's say, Laplace transform of this f function is equal to capital F of s. Then limit of f as s goes to positive infinity must be equal to 0. Okay. So now from here, where do we use this theorem? Okay. Now if you are given a kind of function in s, all right. So actually we use this theorem to determine if that is a Laplace transform of some function or not. All right. Actually, in this case, we will, because sometimes you are given a kind of function in S, okay? By using that inverse operation, you may try to get f. But actually, you may try this, but you may do a lot of calculation and you just end up with nothing and decide that or conclude that, oh, this thing has no, this is not a Laplace transform of any function. As a kind of shortcut, if we know this theorem, just check it out here. If we calculate this limit, if it is not equal to 0, simply say that it's not a Laplace transform of any function. Okay? Because for this thing to be the Laplace transform of any function, limit of this function as s goes to positive infinity must be equal to 0. As you see here, this thing, right, as s goes is infinity, for example, the first one, let's say a here, limit as s goes to positive infinity, s over s plus 1. And we know how to evaluate this. That's equal to, what is it? If you divide by s, right here we have 1, 1 plus 1 over s, that's equal to 0, that's equal to 1, right? So that means that that is not a Laplace transform of any function. Why? Because this is not equal to 0, right? Another one, how about b? Again, if you divide numerator and denominator by s, here we have 1 over s plus 1 over s, right? And as fs goes to positive infinity, this will go to 0 as s goes to positive infinity. Okay, because this is 0, this one is infinity, 1 over infinity is equal to 0. Okay. And how about this one? If you divide by s squared, right, here we have 1, here we have 1 over s plus 1 over s squared, and also actually it's not defined. And also that is not a Laplace transform of any function. And also in a similar way, when s goes to positive infinity, it goes to positive infinity. Also that is not a Laplace transform of any function. That means that if you just pick any function that is defined on this interval, that is piecewise continuous and of exponential order, if you evaluate this Laplace transform, it is never equal to this. Okay, that means this. All right.